All right, so I will, first, tomorrow there will be a problem session. I've also posted an exercise sheet. We'll talk about it tomorrow, whoever wants to come. So the problem set is due in a week from tomorrow. Are there any other questions before we start? All right, so today I will cover Professor Werner for the lecture. I will first tell you in more detail about a general teleportation scheme, about actually all tight teleportation schemes, for not just for qubits but for d-dimensional systems. And so this involves a little bit of formalism that frequently appears in quantum information theory, like maximally entangled states, basis of maximally entangled states, and also basis of unitary operators, which is also partly covered on the exercise sheet. So some of the developments will refer to the exercises. And in the end, I will talk about the dense coding protocol, which is like a very close cousin of the teleportation protocol. And so that's the plan for today. If you have questions at any point, please don't hesitate to ask. All right. So let me just recap about the goals and the setup of the teleportation protocol. So this was already in section 2.6, quantum teleportation. And I hope I will remember to write in a bit bigger letters than I do now. So the goal is to transport or to transfer or to teleport an arbitrary quantum state. So a quantum state which is not known to Alice. I mean, so Alice would like to teleport a quantum state from location A to some other location B without knowing which state to transfer. I mean, if Alice and Bob already knew that they have to transport a particular state, then, well, Bob just would have to prepare this particular state at his location. But the protocol should work for any quantum state. I mean, that's the general thing. If you would like to, for two parties to communicate, you would like that the communication protocol can transport any message out of a set of messages. So it would faithfully communicate any message out of this set of messages. So what we would like for this protocol to have, it should transport an arbitrary one can also call this an unknown, but basically it means that the protocol should work for any state. An unknown quantum state rho. Let's say that this state lives on a Hilbert space, which I will call H sub x, from some party Alice to some party Bob, from Alice to Bob, and so what quantum teleportation refers to is that we have certain resources available to accomplish the task using the following resources. So in this case there are two resources. The first one is Alice and Bob are allowed to share a quantum state which may be correlated, or it will turn out that this protocol only works if the state is like strongly correlated. It has to be entangled or even maximally entangled. So Alice and Bob, they share a state, a shared state which I call omega, distributed to both parties. So this is a state which lives on the tensor product of Alice's Hilbert space and Bob's Hilbert space, which I denote by HA and HB. And also, during the protocol, Alice Alice wants to send the state to Bob, and the other resource that I give them for free is a noiseless classical communication channel. So Alice can send classical messages like numbers or letters or whatever to Bob without any noise. So noiseless classical communication. And just in one direction, so Alice may communicate to Bob, but not the other way around. Let me just set up again what Professor Werner said last week about how such a protocol may look like. So what can the most general protocol look like that uses these resources? Well, there is Alice and Bob, and they share a quantum state. This is one of the resources given. And Alice also has a quantum state on a system X. In this state rho X, and the protocol should work for all states rho X. So, what is the most general procedure that Alice and Bob can apply given these resources? Well, so since Alice can communicate a classical value to Bob, she needs to obtain this value from her systems, and the most general way to obtain a classical value from classical data and throws of dice and from quantum systems is to apply some operation on these systems which returns a classical value. So Alice can apply some operation on the systems that belong to her side. So this operation should output a classical result. Let's call this A, little a. And also, what we care about is we care that in the end, Bob should have the state rho that Alice started with. So in what we care about, these systems are in the end irrelevant. We just care about what state Bob has on his side. So we don't care about the state of Alice's system after the protocol. So basically, let me write this down. So the state of Alice after the protocol, this is irrelevant. So, one can, for example, say that after whatever Alice does, we should trace out her systems and just keep the classical value which she sends to Bob's. So this is exactly captured by the notion of a measurement, like the notion of a POVM. So basically the most general thing that Alice can do, which satisfies these requirements, is that she performs a measurement. So this means a measurement, which I call F. It consists of operation elements F sub A, positive semi-definite operators that add up to the identity on the systems or on the Hilbert space Hx tensor Ha. Okay, so Alice obtains this value A. She sends it to Bob using this noiseless classical communication, and then Bob can do the most general quantum operation on his system, and additionally, this quantum operation may actually depend on this index A. It cannot depend on anything else. That's just the most general procedure he can perform having a classical input. So then Bob applies an operation, most general operation, And that's just a channel on his system. So this is an operation, T, which may, I mean, the operation here applies may depend on A, and it should just be any general, the most general quantum operation that maps his system on the Hilbert space HB into the Hilbert space of X, because we would like to obtain, the state rho which lives on that Hilbert space. So it should at least live on this Hilbert space Hx again. All right. So given these resources and the task to do, this is the most general protocol. And now, if we would like to for this protocol to succeed like exactly, let's just write down the requirement which we would like to have. So I'll put the down again. So what we want is, we want to find a state omega AB. Also, we need to find the appropriate Hilbert spaces of Alice and Bob, which allow us to do this. A measurement F, described by these operation elements, and also these teleportation channels or recovery channels. So a set of quantum channels indexed by these measurement outcomes such that so what do we want? We want that the state rho x together with this resource state if we apply a measurement on Alice's side, so we take the state, we apply a measurement Fa, so the measurement is being applied to the X and the A systems. So let me write it like this. So this F operator acts just on the X and the A systems. It's kind of, that's what we wrote here. And nothing happens to the B system. So the identity operator is applied to the B system. And the way we compute post-measurement states is we take the trace over the systems which are measured, X and A. All right. So after the measurement, we obtain a measurement outcome A, and a state on B survives. This is the post-measurement state on Bob's side. And well, this is the state that Bob has. And Bob can apply his operation, which depends on the value A that he has received. And hopefully this is equal to rho for any rho that you could like to transmit, so for any quantum state on the system X. So this is not quite correct yet. Can anyone see why not? So there is a free variable on the left-hand side. The measurement outcome A. So usually this measurement, a particular outcome A doesn't occur with probability 1. We want that. So, we don't actually care what message was sent. We just want that for any outcome, the state should be rho. So, this means so the state on the left-hand side is not normalized. It is the probability that we get measurement outcome A, but since we don't care about the measurement outcome, we just want that in the sum, the state rho should be transmitted. So this is the so-called teleportation equation. So then our task is to find a state and a measurement and channels such that this works. And I mean, it's non-trivial that such operations exist, but they do. And I will show this in a minute.
Do we need sum over A, or why not put just for every A we want this thing?
So usually, so the reason for this is that we basically want that for every A we get a row here. But the problem is that this has trace 1, and this matrix doesn't usually have trace 1. The trace of this matrix is equal to the probability that you get measurement result A. So basically we want that, well, I mean, another way to say this is that this here should be proportional to rho up to a scalar factor for every A. This has the same content, because it means that for every A there exists a scalar factor here, which must be positive, then, I mean, as one can show, and then the same statement holds.
But it seems that the second statement is actually stronger than the sum statement.
No, it seems like it, but it's not true. The way to see this is, you can require this for all states, but you can alternatively require it for all pure states. And if you require it for all pure states, it will be true for all states, because every state is a connect combination of pure states. But if there's a pure state here, so if you would like to write a pure state as a sum of other positive operators, then each of the operators has to be actually proportional to the pure state. I mean, we talked about the extremal points of, well, I can explain this better or more if you like, but okay. So these statements, the equality here or this for every A is actually equivalent. But it's not trivial to see. Okay. So I hope this is clear. Before I show how to make up such a scheme, I would like to show that this is equivalent to the teleportation equation that Professor Werner wrote down last week. So if you look into your write-up from last week, the teleportation equation looked differently, and the difference is that my channels operate in the Schrödinger picture. They act on states in the input space and map to the output space. Let me just show you the equivalence. So what we wrote down, last week was kind of the following. So last week we wanted an equation that holds for all rows and for all measurements you can perform on row. So we wanted for all row and for all measurements, which we call G. We wanted to have that the trace, so let me start from the right hand side, the trace between rho and this G of B, an operator. I mean, so if this equation is true, then let me just continue, like what will be true then. So this is then equivalent to the sum over A, the trace TA. I'll just write down the same stuff. Times G of B. Alright, so if the above equation holds, then also the lower equation holds. And now we transform the right-hand side into the form which we had last week on the board. So this is the same as, if you remember the definition of the transpose channel, this was given by the fact that you leave this here and you put the map over with a star. So this is now a map kind of acting in the Heisenberg picture. It acts on operators on the output space. And So by definition of the partial trace, this is the same as you take a trace over all systems. So this is just a trace over the B system, but now you take a trace over all systems, and we write down this operator here. So let me now write it down. This is the operator rho x, omega b, one b. All right, so this is this operator, and we multiply it with TA star. Well, we multiply it with the identity operator. So this is the operator which lives on B. We multiply it with the identity on XA times TA star of GB. So this is kind of the definition of the partial trace. Instead of doing the partial trace times some operator, we take everything inside the partial trace and put the identity over the systems. So that's kind of the definition. But now this here is just, I mean, these two things are easily multiplied. This is FA, XA, tensor, should be tensor product here, P star A. So this was the teleportation equation which was on the board last week. The teleportation equation from last week was that this here should be equal to that for all rho, but also for all measurements you can do on the final state. If you want to write it in the Schrödinger picture, then you can, in the Heisenberg picture, then you can just have an equality between numbers, like the outcome probabilities. Whereas in the Schrödinger picture, we had an equality between states, so that's a bit easier to formulate. Any questions about this? So let me now write down a scheme which does the quantum teleportation, and we will verify that this scheme works. Okay, now show that this can be done. And before I really show you the construction, we need to introduce a technical tool which is called technical tool. So we need to introduce a notion of a basis of the matrix space which of unitary operators which are orthogonal to each other. So orthogonal orthogonal basis of unitaries. So this is what it's called. So a set. So we have a set of unitaries. A goes from 1 up to d squared. These are all elements of a d-dimensional complex vector space. Okay, let's think about this. We have a d-dimensional vector space, and the operators on that vector space, these are basically just complex d by d matrices. So this is can be seen as a complex vector space of dimension d squared. So if we would like to have a set of linear independent operators which forms a basis, then this basis has to have d squared elements. And we would like, I mean, it's easy, of course, to write down many such bases. The non-trivial constraint is that we would like to have a basis just composed out of unitaries for a reason which will be apparent in the construction later. So such a set of unitaries unitaries UA is called an orthogonal basis. Orthogonal basis of unitaries if the following holds. So the condition is that they should be orthogonal, or like orthogonal with respect to some appropriate inner product, and the appropriate inner product is this here. The trace of UA star, UA prime, so we take two unitaries, UA and UA prime, and then the inner product defined by the trace of the first thing star times the second one. This should be just the Kronecker delta between A and A star. So I'm not sure if we've talked about the fact that this defines an inner product. It does, and we normalize it by the dimension because we want, if we have a unitary here and the same unitary here, then we are taking the trace of the identity matrix, which is D. So if we divide by D, we get just 1. So this is called an orthogonal base of unitaries if this holds. It also turns out if this holds, then they are linearly independent. This is not so difficult to see. So it is if you think about it, it is not trivial that such a set of unitaries at all exists. But on the I've written down the most famous example of such unitaries on the exercise sheet. This is exercise number 3, and you should verify that they satisfy this equation and also satisfy a bunch of other stuff. So existence is, for example, on exercise sheet 4, problem 3, like the standard example is that U, K, L, the following unitary R goes from 0 to D minus 1. Let me just follow the same convention. Pi I over D, RL, so you asked to verify this, yeah. So it's a bit surprising that they exist. If you count the number of parameters that you have in the unitaries and the number of constraints you have in this set, I won't do the counting here, but I mean the naive counting would say that it's unlikely that such things exist, but they exist in abundance actually. All right. So let's for now assume that they exist in every dimension. Or, I mean, you will verify this. So now the construction. Of a teleportation scheme. Is as follows. We choose, I mean, we are given the vector space of the state which we would like to transmit, like the vector space Hx. So what we do is we define the vector space of Alice and the vector space of Bob to be just of the same dimension. And let's assume that this is a d-dimensional vector space, a Hilbert space. So by d I will now denote the dimension of this thing. I will also construct a scheme where the number of measurement outcomes is d squared. So number of measurement outcomes is equal to d squared. This will be related to the index of this orthogonal basis of unitaries. Then as the state between Alice and Bob, we can choose any maximally entangled state. So choose the state that Alice and Bob share initially. Choose this to be omega with any maximal entangled state. So omega on the on d-dimensional systems between Alice and Bob. So maximal entangled, I mean, an abstract definition of this term means just that if you trace out one of the systems, for example, Alice's system, from the maximally entangled density matrix, then you get the maximally mixed state on Bob's side. So maybe it's not surprising that for this teleportation scheme we actually need to use the maximally entangled state. Okay. Let me just write down all elements of the construction and why it works. We will do the computation in a minute. So oftentimes people say the maximally entangled state, but actually there is an infinite set of maximally entangled states, just as many as there are unitaries. And for the measurements that Alice is performing, we also choose a measurement on a basis of maximally entangled states. So in the following sense. Choose measurement operators in the following way. So these operators Fa I define to be phi A, where phi A is just defined to be the application of the unit of one of those unitaries, the unitary UA, to the first half of the maximally entangled state from before. All right. So, and a lemma which you're going to verify. Lemma. So this is exercise 4.3, I think, part C, is the following. If you have such an orthogonal basis of unitaries, then this here is an orthogonal set, an orthonormal set of maximally entangled states. So this set Fa, where A runs from 1 to d squared, is an orthonormal set. Orthonormal, or is an orthonormal basis even of the vector space of the Hilbert space of between Alice and Bob, consisting of maximally entangled states. You have to prove it in this lemma. Let's put a QED sign here. And again, not surprisingly, the correction operation that Bob has to apply is again related to these unitaries. So choose these channels TA applied to a state sigma, let's say, to be the unitary the unitary conjugation of sigma. So this generalizes the construction by 4 qubits. Like the standard construction for qubits. And if you would like to see a very nice illustrative treatment of this case, this is given in Nielsen and Zhuang's book. Like in modern language, this is given in Nielsen and Zhuang's book in section 1.3.7. Without actually using much of quantum formulation. But, I will now show that this scheme as specified satisfies everything that we need. And I mean, the computation will be a little bit detailed, but I think it is worthwhile that we go through it, because such computations often appear in scenarios where you have several systems in tensor products. You need to be very careful on which systems to apply some operators. So that's why I want to show you the computation. So now, verify that the general d-dimensional scheme works as promised. And so there's again, whenever you are computing with the maximally entangled state, or let's say with a maximally entangled state, there is one computational trick that is oftentimes employed. And this, I think this was proven in the last session by Professor Werner. It's also, I think we used it before. So we need the following like fundamental trick. This is if we apply an operator on one half of a maximally entangled state, then we could alternatively do nothing on the first half of the maximally entangled state and apply the transpose of the operator on the other side. And as you may know, or as we may have said, is the transposition operation is also not unique. It depends, it's a basis-dependent notion, just like the notion of a maximally entangled state is basis-dependent. And so the basis with which you transpose the operator is the same as the basis with which you write down the maximally entangled state. And if you write down this here as the sum over I, then this basis I would be the one with respect to which you do the transposition. Okay. As I said, let's now do the computation. So one way is to write out everything in terms of like basis vectors like I and j, but by using this trick we can actually avoid it to a large degree. So let's verify. Let's write down the complicated side of the teleportation equation, maybe without the sum, and just see what comes out. So this is the trace, that's A. We take rho x, tensor the maximally entangled state between Alice and Bob. Alice performs her measurement with outcome A. Let's see. Nothing happens to Bob's system. Yeah, so that's the state which Bob will have, and Bob applies the channel TA to it. And maybe, well, okay, and we have a sum over A. So that's the complicated side of the teleportation equation. Now let's just plug in everything. So this is the same as sum over A. The channel was just defined to be the unitary conjugation with UA. UA is applied to everything. So the trace of XA. So I indicate the systems that we are operating by these indices X, A, and B, just to keep track of everything. So like, I mean, okay, let's just be clear. So this is a state on row X and a maximally entangled state on AB. Whereas these Fs, these are basically also made up of maximally entangled states, but on the X and A systems. So this maximally entangled state and this maximally entangled state, they overlap on the A systems, but the other half is on different systems. So one has to be really careful with such computations. So, but let's just do it. So this is row X tensor omega on AB. Now F was just also the maximally entangled state rotated by some unitaries. So this is the unitary A applied to the first system, to the X system. Nothing happens to the second system. The maximally entangled state on XA. The unitary on the other side comes with a star. And there's a tensor of the identity on P. I take the partial trace of this. And the UA star from the channel comes on the right. So I think all of this is correct. Okay, so what we now do is, let's put the unitary onto here by this rule, and it becomes the unitary A X transpose. So our goal is basically to annihilate this unitary and this unitary. And in order to do this, we have to shift this unitary from the X system to the A system, then from the A system to the B system, because the B system is the only one which is left over, and hopefully it will annihilate. So, but for now we have the transpose of the unit of this unitary, and if we shift this unitary here, we also get the transpose. X star and the transpose, basically. Okay. Now we use that the trace is cyclic. So now we would like to shift the unitary even further. So, sorry, now the unitary acts on the A system. Let me put an A here. We shift it from the X system to the A system by the rule above. Now we would like to shift the unitary from the A system even further to the B system, but we can only shift it or move it around the maximally entangled state. So we use that the trace is cyclic to take this unitary in front of everything, and then we can use this maximally entangled state to shift it one further. Okay, let me write. So this is the same as the sum UA, trace. Okay, this is, now we have the identity on X, tensor UA A star and transpose, and we do nothing on B. So this is essentially this part. we have now moved it here to the left-hand side by simplicity. Again, we have the identity on X. On X, tensor the unitary on A transpose. Nothing happens on B. Okay, so this is this part. And what is left is now the maximally entangled state on X and A, and nothing happens on B. All right. Do you agree that this is the same? So one has to be a bit careful here. The trace is cyclic, but the partial trace is not, generally. So this is a mistake that is sometimes made. The partial trace is only cyclic if you move the identity operator from right to left, and this is what we did. So the B system is not traced out, but there is an identity operator on the B system anyway. So if you do this in terms of like matrix units or something like this, you will see that this is correct. But in general, it's not correct. Okay, now we put this operator on here, so this becomes UA on the P system. We have a dagger, and now we have a transpose and another transpose, so the transpose goes away. Same thing happens here. Becomes P. Yeah, transpose goes away. Okay, so now we don't even trace over the B system, but there are some unitaries acting from the left and from the right here, but they are not traced over, so we can take them out of the trace. So we get some UA. I mean, these are unitaries on the B system essentially. There's a dagger. Trace identity on X and on A. Oh well, I mean, we took the unitaries out, so this part was already taken care of. Row X tensor the maximally entangled state on AB, and the maximally entangled state on XA tensor the identity on B. Out. This is UAB, UAB star. Now, this here is of course the identity operator, because U is a unitary, so we really need that U is a unitary in this case. And so what we're left with is, let me write it down here. Entangled state on XA. So now the effect of the unitary has gone. So we needed the unitary in order to get a measurement basis, in order to get orthogonal. I mean, these operators, F, they are basically equivalent to pure states, but we needed a lot of pure states to make up the measurement. That's why we needed the unitaries and the unitary corrections, but effectively we now got rid of them. And now what would remain to do is to evaluate this term. I mean, I could, so my way of evaluating this would now to write omega in terms of like sum over I and j and stuff like this. I'm not sure if I should do this. I can tell you the interesting part of the result, or I can do the computation. Would you like to see the full computation or just? So, the interesting part of the result is the following. So it turns out that this is equal to 1 over d squared times rho x. So the 1 over d squared comes from the fact that, I mean, for example, if you write that omega is 1 over d, sum ij from 0 to d minus 1, j. And because we have two omegas, we get a 1 over d squared. So this tells us that each of the measurement outcomes A occurs with probability 1 over d squared. But I mean, no matter which measurement outcome we get, the state after correction is actually independent of A. It does the right thing, just not with the right probability. But I mean, since we get some measurement outcome at some point, I mean, in each run we just sum everything up and we get rho of x. So I think this answers your question from before. With this scheme, any particular measurement outcome is obtained with probability 1 over d squared. And the protocol does the right thing in this case. So this kind of shows that there is such a construction. And the construction really hinges on the existence of such a basis of unitary operators, which are, so we need that they are unitary such that they cancel in the last step, and we need that they are orthogonal such that the measurement f is really a measurement. So it's like, these are operators which sum to the identity. That's what we need. So this construction may now look very special, but a theorem which I'm not going to show, but I still am writing it down, is that this construction is essentially unique. At least it's unique among the minimal constructions. So the theorem is the following. I mean, in order to show the theorem, you have to do computations like this, but be much more careful about like how much freedom you have in doing such computations. I mean, it's not, yeah, one has to be very careful and a bit clever. So the above construction is essentially unique. So, and this is a theorem which Professor Werner has proved. Theorem. So there is a cool paper which contains a lot of this technical stuff about basis of maximum entangled states and orthogonal unitaries, which I've used this paper like in several different works. So I'll give you the reference. This was published in the Journal of Physics A, volume 34, a long time ago. So it says the following. In the case when Alice's and Bob's Hilbert space are the same as the Hilbert space, I mean the same size as the Hilbert space of the system which you would like to transmit, and of finite dimension, so this is also a requirement, and f is a d squared outcome measurement. So So one can show that one cannot get by less than d-squared outcomes. Well, actually this would be a consequence of the theorem. I can state this as a corollary. So if one takes a d-squared outcome measurement, then for any teleportation scheme, for any teleportation scheme. So what is a teleportation scheme? As I haven't introduced it formally, but it's given by such a state, by such a measurement, and by a collection of recovery channels. I mean, this obviously is necessary data to specify the scheme. For any such schemes, there exists an orthogonal basis of unitaries denoted by UA. And so these are, I mean, in d dimensions obviously, and a maximally entangled state, and a maximally entangled state, omega, such that I mean the scheme looks like what I've written before, so such that the state that Alice and Bob shares is this maximally entangled state. The measurement is obtained by acting with the unitary on this maximally entangled state. And the recovery channels are just the unitary conjugations. So, in this case, the construction has to be just the way we have done it. So all such teleportation schemes are basically indexed by orthogonal basis of unitaries. There is a little bit more freedom in the maximum entangled state, but this is just a relatively trivial freedom compared to this one. So, as a remark, this shows that at least in the case where the Hilbert space dimensions of Alice and Bob are equal to the dimension of the system which you would like to transmit. So there are some arguments why this is the minimal dimensions. So in the case that you choose the Hilbert space dimensions minimal, then the number of measurement outcomes has to be d squared. I mean, you have to use a full basis and each of the elements is not trivial. So one has to, so in this case one has to have at least, d squared classical values. So it kind of means that if you would like to transmit an arbitrary d-dimensional quantum state with the help of classical communication, then the number of classical values has to be the square of the dimension of the quantum system. Or if you take the logarithm of d squared, this is twice the logarithm of d. So, I mean, we haven't talked about channel capacities, but it means that so log d is the quantum capacity of this quantum communication channel. It's defined to be a logarithm of the dimension of the Hilbert space. And the needed classical capacity has to be twice as large. So the number of classical signals, log of this, has to be twice the quantum capacity in this protocol. So it means that in order to transmit a d-dimensional quantum state, you need a d-dimensional maximally entangled state. This was our first resource, omega LB. And you need twice the capacity of a classical channel to do this. This has been proven to be minimal. And also it kind of follows from the theorem. Okay, I will talk about dense coding in a minute, so I will make this point a bit more explicit. Let me tell you about a few open questions which are related to this field. So, as I said, as this theorem says that minimal teleportation schemes are essentially classified by basis of orthogonal unitaries, but there is no exhaustive classification of such bases. Yeah, so this is a problem which is actually related to a bunch of other problems in mathematics, and I will outline this now. I've shown you, or you will show in the exercise sheet, that such a basis exists in every dimension. At least one basis exists, but to characterize all such bases, this is an open question. So let me write this down. So there is no exhaustive classification of orthogonal bases of unitaries exists, or at least as of yet. This doesn't exist, but a very prominent example, which has been employed also in the theory of error correction, comes from a construction called shift and multiply basis. So, general class, or one class of constructions. So this is called shift and multiply. For a reason which you will shift and multiply. So how do we define this? Let's say we define it like this. So we would like to define a set of d-squared unitaries, and let's do it the way that these unitaries are indexed by indices I and j, and each of those indices runs from 1 to d. So these unitaries have a particular structure. And so these are unitaries in d dimensions. And the way they are defined is you multiply the vector by a phase. So this is the multiply part. Let me call the phase h, j, I, k. So the phase depends on which unitary you take and on which basis element you act on, and then it also shifts the basis element. This depends on j and k. So this is a complex number. Each of those is a complex number, and lambda and k is also a number, of course, between 1 and d. And lambda is a function from 1 to d times 1 to d, 1 to d. Okay, so you multiply the basis elements by a number, and you also shift the basis element. Depending on k and which unitary you shift it to another one. So, and there is a proposition which is not very difficult to prove. It's in the same paper as above. So this definition defines, this definition depends on these numbers, and it depends on this function lambda. So this defines an orthonormal set, orthonormal orthonormal basis of unitaries. Unitaries if and only if. I mean, so this ansatz is already a little bit special. So there's a little bit of structure in this ansatz. A general orthonormal base of unitaries may be even more general, but such a shift and multiply thing is an orthonormal base of unitaries if and only if two conditions are satisfied. So each of those matrices H, so each matrix H, J, so J runs from 1 to D and has matrix elements Hj, indices I and k. So each is a complex Hadamard matrix. Hadamard matrix. So this means that all entries are of Hj, Ik are of modulus 1. So they're just complex faces for all Ij and k, and they are unitary. Well, I mean, they can't be unitary, but up to a factor. I mean, a matrix with this requirement cannot be unitary. So I'm not sure if you have heard about the problem of Hadamard matrices. Like the most famous problem is real Hadamard matrices. So these are real matrices which have entries plus and minus 1, and they are unitary, or let's say orthogonal in this case. And so this is a very famous problem from combinatorics, because the set of D by D matrices with entries plus and minus 1 is just a finite set. And the question is, for every dimension, does there exist a real Hadamard matrix? And there's just a finite number of matrices to check, although the number of matrices you have to check is 2 to the D squared. So really big one. And so are you familiar with this conjecture? I mean, the famous conjecture is that for every dimension which is divisible by 4, there exists a real Hadamard matrix. And so far, people have checked this up to dimension like 600, but it's an open question. And so the complex case is completely different from the real case because it has this continuous spectrum. But the question is, the question to classify all complex Hadamard matrices is still open. On the exercise sheet, you kind of see that in every dimension there is a complex Hadamard matrix, although not in every real dimension there's a real Hadamard matrix. So this is a little bit of an open question, the complete classification is open, and the requirement on lambda. So lambda is a Latin square. So a Latin square is just a square, a d by d square, such that in each row and each column, each of the numbers 1 to d appears just once. So in mathematical terms, this means that the function which maps k to lambda of k comma l and the function which maps k to lambda l comma k, these functions should both be injective for every L. It just means that in every row and every column, every number is just appears once. So this is R, and these are injective for every L. You probably have heard of the Latin squares, I suppose.
What is the German word?
Lateinisches Quadrat. There's this very famous
Zauberquadrat nennt das auch.
Kann sein.
Da gibt es so einen Kupferstich oder was?
Genau, von Dürer. Der ist ein ganz berühmter Kupferstich von Dürer.
Ich kenne das als Zauberquadrat.
Kann sein. Vielleicht ist es ein besonderes lateinisches Quadrat. But it's an open problem to enumerate all Latin squares of a size, of a certain size. Well, okay, if you're interested in the proof of this theorem, it's in this paper. It's also not, you just basically compute it. And the standard construction is in exercise 4.3. Do you have any, questions on this part anymore? If this is not the case, I would like to show you just a very related protocol briefly, and you will actually, it more or less follows from the exercises that how this works and that this works.
Yeah, I actually have a question for this part. Is it, if we would know more orthogonal systems for unitaries, would it be of any use actually?
I think some error correcting codes are based on such unitaries.
But connected to teleportation, it's like.
I'm not so familiar with teleportation, or maybe this is more like a mathematical question, but for some error correcting codes this is relevant. And another question which people, would be people in quantum information theory, but even people in the classical signaling community would be highly interested is what we call the SIG POVM problem. Well, like phrased in classical terms is, if you have a complex vector space, you would like to find d squared unit vectors which have all equal angles with each other. So if you take two vectors from these d squared vectors which are not the same, if it's the same vector, then of course the angle is 0. But if you take any two vectors, you would like that the inner product between any two vectors is the same for these d squared. And the question whether such a thing exists is an open question. And some special constructions are based on because also of d squared, stuff like this. So this would be a highly, this is a major open question basically in complex geometry. And it's, I think, there are deep relations to this question, although I'm not so familiar. So the other protocol which is very much related to teleportation is dense coding. It's called dense coding. Some people call it super dense coding. I don't know why. But anyway, so let me write this as a kind of a new section, although it will be pretty short, brief. 3.7, dense coding. Dense coding. So with teleportation, what we did there is we used entanglement and a message of size d squared, a classical message, classical communication, and we achieved quantum communication of a d-dimensional system. So it kind of shows that the sum of these two resources is at least as valuable as this resource. And dense coding shows kind of a converse to this. So it says you again use entanglement, so Alice and Bob share entanglement. And they are able to communicate a quantum system, so to physically transport a quantum system from Alice to Bob. There is no, in teleportation, there is no physical transfer of a quantum system. There's just this classical communication. And CD, quantum communication. And we can use these two resources to communicate one of these squared messages. it work? It basically works like the teleportation protocol, except that Alice applies Bob's operation and Bob applies Alice's operations. So protocol is swap Alice's and Bob's equipment from the teleportation protocol. So Alice and Bob, they share a maximally entangled state. And now, if there's just one, like a particular maximally entangled state, which they share. Then d-dimensional, maximally entangled. And so in the first step, instead of performing a measurement on her side, Alice applies one of those unitaries. If Alice wants to send message, a particular message A from the message set of p squared elements, then she applies UA. So this means that the new state, the new state of both is Alice applies one of the unitaries, Bob does nothing. So, and what you kind of need for this protocol is that, so Alice applies this unitary, and depending on which unitary she applies, all those states are pairwise orthogonal. So if Alice and Bob share the maximally entangled state, then by unitary actions on just Alice's side, she can achieve d squared independent states, d squared orthogonal states, even though the size of her system is only size d. So they are mutually orthogonal. Mutually orthogonal. This is what we needed in the previous protocol, but you, as I said there, you have to verify this in exercise 4.3c. So this is basically the whole magic. Even though Alice has only access to a d-dimensional system, which she can later send, she can achieve one of d squared orthogonal states. Then, in the second step, well, after Alice has done this, she sends her d-dimensional system to Bob. Bob already has like a d-dimensional system. So Alice sends her system to Bob. Well, now Bob has both parts of a d squared dimensional system, and it's in one of these squared orthogonal states, so we can just perform a measurement in the basis of these states and finds out which one of the states it was. Bob measures so it's just earlier I called this phi A. Just measures this. And so I guess it's quite clear to every one of you. He gets an outcome, and this outcome agrees with Alice's message for sure. So there is as before, there is a similar theorem that all dense coding schemes in these minimal dimensions are essentially like this. So this works and is essentially unique. The theorem is for HA equals HB equals quantum systems of minimal dimensions for this task, and p squared classical messages all schemes are parameterized by orthogonal basis of unitaries in this way. All dense coding schemes are parameterized by, let's say, UA, etc. So this also means that for this minimal setting, every dense coding scheme is in one-to-one correspondence with one teleportation scheme. They are really just obtained by swapping what Alice does and what Bob does. Yeah. This is already what I wanted to say today. I think in the next weeks, Professor Werner wants to talk about like tasks and resources, but not in the exact setting. So everything was about like, we would like to perfectly transfer a quantum state, or we would like to transfer a message from Alice to Bob with no probability of failure. I think in the next weeks, the plan is to extend these protocols to the scenario where you allow a little bit of error, and to see whether you can get by with much less resources. For example, whether you can transmit a d-dimensional quantum systems up to error epsilon, and we have to define what error epsilon is, with much less classical communication, for example. Stuff like this. So this is to come. Do you have any questions on this part? If not, then let's finish.